Barely recognizable Olympic swimmer Schmeichel Phelps back to talk to you about similarity transformations. And I swear, if one more of you calls me Michael Phelps, I am out of here.
First thing we're going to talk about is a similarity transformation. That's transforming or changing the dimensions of an object in space to create a similar object. So a transformation, that should sound familiar because we already dealt with transformations. And when we dealt with transformations, we talked about reflections, translations, and rotations. But those were congruent transformations, meaning they were transformations that you perform on an object and you get a congruent figure afterwards. When dealing with similarity transformations, however, you perform that transformation on an object like parallelogram EFGH, and you end up with a resulting image like parallelogram ABCD, where they are not congruent to one another, but they are similar to one another. And we'll talk more about specific types of similarity transformations in a second. Now, a dilation is a similarity transformation that enlarges or reduces the original figure proportionally. Now, if you take a look at our example down here, and we take parallelogram EFGH to be our pre-image, we're going to perform a dilation on this parallelogram with point Q as the center of dilation. And the result is this image over here, parallelogram ABCD. And we can see that parallelogram ABCD is actually similar to parallelogram EFGH, meaning that all pairs of corresponding angles are congruent and all pairs of corresponding sides are proportional. And because this parallelogram, this pre-image, undergoes a dilation or similarity transformation that enlarges it to become this image over here, it becomes an enlargement, and we'll talk about that more in a second. Now, a scale factor of dilation is the ratio comparing a length on the image to a corresponding length on the pre-image. So this is actually pretty straightforward. A scale factor of dilation is just any ratio comparing the length of a side on the image to its corresponding side on the pre-image. So if we were to create a ratio with the measure of segment AD over the measure of segment EH and simplify that down, that would be the scale factor of dilation. And you should get the same thing if you were to create a ratio with the measure of segment AB over the measure of segment EF and simplify that down. Same thing with the measure of segment BC over the measure of segment FG and simplify that down. Same thing with the measure of segment CD over the measure of segment GH and simplify that down. Remember, the scale factor of dilation requires that the length of a side of your image is over the length of your corresponding side of your pre-image. So image over pre-image in order to create your scale factor. Now, an enlargement is a dilation with a scale factor greater than 1. In an enlargement, the image will be larger than the pre-image. So as we said earlier, if we take parallelogram EFGH to be our pre-image and we perform a dilation on it with point Q as the center of dilation and parallelogram ABCD is our resulting image, then clearly parallelogram EFGH has undergone an enlargement. And you could always confirm this by creating a scale factor of dilation. And the way you do that is you take the measure of one side of your image and put it over the measure of the corresponding side of your pre-image. And when you do that and simplify it down, that ratio, that scale factor, should be greater than 1. Now, a reduction would be a dilation with a scale factor between 0 and 1. In a reduction, the image will be smaller than the pre-image. So this time, we're taking parallelogram ABCD to be our pre-image, and it's undergoing a dilation with point Q as the center of dilation, and our resulting image is parallelogram EFGH. Now, as you can see, our parallelogram has gotten smaller after that dilation, meaning that it must have undergone a reduction, and you can confirm this by creating the scale factor of dilation, which involves taking the measure of a side length of your image and putting it over the measure of the corresponding side of your pre-image. And if you simplify that down, that ratio, that scale factor, should be between 0 and 1.
Come on with Schmeichel Phelps and swim right into this example.
Now, example 1 says determine whether each dilation is an enlargement or a reduction. Now, these type of questions are pretty straightforward. We are going from our pre-image, which is an undilated pupil, to our image, which is a dilated pupil. So because the resulting image is larger than our pre-image, we can call this an enlargement. Part B, we again have a pre-image and an image, but this time our pre-image is larger than our image. So our pre-image is getting smaller as we go to our image, meaning this must be a reduction. And you could always confirm this if you create a scale factor of dilation, meaning you find the measure of this side length and put it over the measure of this side length. If you get a ratio that is between 0 and 1, you know that it must be a reduction, which this is. Now, example 2 says determine whether the dilation from A to B is an enlargement or reduction. Then determine the scale factor. Now, the first and most important step in each of these problems is to determine which of these figures is your pre-image and which is your image. Well, this is going to be a dilation from A to B. Because we're going from A to B, that means A must be our pre-image and B must be our image. After that, we have to determine whether the dilation from A to B is an enlargement or a reduction. To do that, we just have to find the scale factor of dilation. If the scale factor of dilation is greater than 1, then we know it's going to be an enlargement. If it's between 0 and 1, we know it's going to be a reduction. So, how do we determine the scale factor of dilation? Well, we take a side length measure for our image and put it over the corresponding side length measure of our pre-image. So, which of these corresponding side lengths can we easily get from this figure over here? Well, this measure over here and this measure over here would require the distance formula. Same thing with this measure over here and this measure over here. But what about the bases? It looks like, because these are horizontal lines, I could easily count the distance between points, meaning I can find the length of each of our bases. So let's do that. The length of our base of our image here would be 1, 2, 3, 4 units. The length of our pre-image base would be 1, 2, 3, 4, 5, 6, 7, 8 units. Sweet, we have now created our scale factor, which we can simplify down to 1/2. Because our scale factor of dilation is 1/2, meaning that it's between 0 and 1. That means that our dilation from A to B is going to be a reduction, and this reduction is by a scale factor of 1/2.
Winning is overrated. Time for you to try.
Okay, doing the same thing here. Remember, our first and most important step is to figure out which of these figures over here is our pre-image and which is our image. Well, we are determining whether the dilation from A to B is an enlargement or a reduction, meaning we're going from A to B, meaning this figure A over here would have to be our pre-image, and this figure B here in blue would have to be our image. Next, we're determining whether this dilation is an enlargement or a reduction. To do that, we have to determine the scale factor of dilation. The scale factor of dilation will tell us whether it's an enlargement or a reduction. If the scale factor of dilation is greater than 1, it's an enlargement. If it's between 0 and 1, it's a reduction. So how do we do that? Well, we take the measure of one side of our image and put it over the corresponding measure of the side of our pre-image. We then look over here and determine, are there any corresponding side lengths that you could easily find the measure of so that we don't have to use the distance formula, because we want that to be a last resort. Well, yeah, you could either use the top of the image parallelogram and the top of the pre-image parallelogram, or the base of the image parallelogram and the base of the pre-image parallelogram. So since we used the base last time, I'm just going to use the base again. Why not? So we'll find the length of the base of our image and put that over the corresponding length of the base of our pre-image. So how do we do that? Well, since they're horizontal lines, we can just count the distance between each of these points, and that would be the length of this side. So in our image, our length of our base would be 1, 2, 3, 4, 5, 6, 7, 8, 9 units. In our pre-image, the length of our base would be 1, 2, 3 units, meaning our scale factor of dilation would be 9 over 3, which simplifies down to 3 over 1, or just 3. Now, because our scale factor of dilation is greater than 1, it's 3, that means our dilation from A to B has to be an enlargement by a factor of 3. Now, example 3 says, is the transformation from triangle KMJ with vertices KMJ to triangle RQP with vertices RQP a dilation? If it is, state whether it's an enlargement or a reduction and determine the scale factor. So anytime you're given vertices, the first step should always be to graph those vertices. So point K is at 7, 6. We go over 7 on the x-axis, up 6 on the y-axis, put point K. Point M is at 7, -4. We go over 7 on the x-axis, down -4 on the y-axis, put point M. Point J is at -1, -4. So we go over -1 on the x-axis, down -4 on the y-axis, put point J. Those vertices create triangle KMJ. Now, triangle RQP has these vertices. So we start with R. Point R is at 5, 2. We go over 5 on the x-axis, up 2 on the y-axis, put point R. Point Q is at 5, -3. We go over 5 on the x-axis, down -3 on the y-axis, put point Q. And then point P is at 1, -3. We go over 1 on the x-axis, down -3 on the y-axis, put point P. Those those points, those vertices, create triangle RQP. Now, what is this question asking us? It's asking us if the transformation from triangle KMJ to triangle RQP is a dilation, meaning is it a similarity transformation, meaning is triangle KMJ similar to triangle RQP? Well, in order to figure that out, we just have to determine, are the measures of the corresponding side lengths proportional? If they are, then the two triangles would be similar by the side-side-side similarity theorem, meaning that this would be a dilation. So the way we're going to do this is we're going to create the scale factor with all three pairs of corresponding side lengths. If the scale factors of each of those pairs of corresponding side lengths are all equal to one another, that means all three pairs of side lengths are proportional, meaning that the two triangles would be similar to one another by the side-side-side similarity theorem again. So how do we do this? Well, again, we want to create scale factors between all three pairs of corresponding sides. So in order to find scale factors, we need to first determine which of these figures is our preimage and which is our image. Well, we are going from triangle KMJ to triangle RQP, meaning that triangle KMJ has to be our preimage, triangle RQP has to be our image. Next, we're going to determine the scale factors for all three pairs of corresponding side lengths and see if they come out equal to one another. So we can pick whichever pair of corresponding side lengths we want to start with first. I'm going to choose segment KM and segment RQ. Now remember, we are finding a scale factor, meaning we need to find the length of a side of our image and put that over the length of the corresponding side of our pre-image. I'm going to find the measure of segment RQ and put that over the measure of segment KM over here. Well, I need to find the measure of segment RQ. Since this is a vertical line, I can just count the distance between each of these points. So the measure of segment RQ would be 1, 2, 3, 4, 5 units. The measure of segment KM, again, we have a vertical line, so we can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. So we have a scale factor of 5 over 10, which simplifies to 1/2. Now we're not done. We can't just call it a day and say, yeah, this is a reduction by a scale factor of 1/2. What we have found is the scale factor between one pair of corresponding sides is 1/2. We have to make sure that the scale factor between all three pairs of corresponding side lengths is 1/2. So we move on to the next pair of corresponding side lengths. We can choose that to be segment JK and segment PR, or segment PQ and segment JM. I'm going to choose segment JM and segment PQ. So again, we have to create a scale factor which involves finding the length of one side of our image and putting it over the length of the corresponding side of our pre-image. So in this case, again, we were talking about the measure of segment PQ. We're going to put over the measure of segment JM. What is the measure of segment PQ? We again have a horizontal line, meaning we could just count 1, 2, 3, 4 units. The measure of segment JM, again, we have a horizontal line, so we can count 1, 2, 3, 4, 5, 6, 7, 8 units. So the scale factor between these two corresponding side lengths would be 4 over 8, which simplifies down to 1/2. Perfect. So we know that the scale factor between these two pair of corresponding side lengths is 1/2, and the scale factor between these two pair of corresponding side lengths is also 1/2. Now again, we are not done. We need the scale factor for all three pairs of corresponding side lengths to be the same. So we now have to check the measure of segment JK and the measure of segment PR. Create the scale factor with those two corresponding side lengths and see, do we get 1/2? Well, in order to create a scale factor, again, we need to find the image side length over the corresponding pre-image side length, which means we need to find the measure of segment PR and put that over the measure of segment JK. Now, the first thing I want you to note is that we no longer have a vertical or a horizontal side length. We have two diagonal side lengths, meaning in order to find the measure of each of these side lengths, we're going to have to use the distance formula. So we can choose either of these to find the distance of first. I'm going to first find the measure of segment JK, and then I'm going to find the measure of segment PR. So the measure of segment JK we find by using the distance formula. We pick one of these points to be x sub 1, y sub 1, and the other point to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the distance formula over here, and we simplify. -8 squared plus -10 squared becomes 64 plus 100, which is 164. We can then simplify that if we were to break it into two radicals that multiply together to make 164, one of which has to be a perfect square. That would be rad 4 times rad 41, which simplifies to 2 rad 41. So that would be the length of this side. side. Now we have to find the length of the corresponding side in our image, the measure of segment PR. To do that, we again use the distance formula. We pick one of these points to be x sub 1, y sub 1, and the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spots in the distance formula and simplify. 5 minus 1 is going to give you 4. 2 minus negative 3 is going to be 2 plus 3, which is 5. 4 squared is 16. 5 squared is 25. We add these together and we get rad 41. Now, rad 41 cannot be simplified, so we just leave it like that. For our scale factor here, it's going to look kind of weird. We're going to have rad 41 as our image length over 2 rad 41 as our pre-image length. Well, what happens here? If I were to simplify this, the rad 41 in our numerator cancels out with the rad 41 in our denominator, and we're left with 1/2. But because all 3 pairs of corresponding side lengths have the exact same scale factor of 1/2, we know that our pre-image and our image triangles must be similar to one another by the side-side-side similarity theorem, meaning that this would be a similarity transformation, meaning it would be a dilation. Now the question is it an enlargement or a reduction? Well, the scale factor of dilation here is 1/2, meaning it's between 0 and 1, meaning it would be a reduction by a scale factor of 1/2.
You know, I recently saw this very inspirational movie, and I want to share with you what they said. They said, just keep swimming. You try.
Okay, doing the same thing here, except this time we're going from triangle ABC to triangle EFG. And we're given the vertices, so anytime you're given the vertices, the very first thing you should do is plot those vertices. So point A is at 3, 7. We go over 3 on the x-axis, up 7 on the y-axis, put point A. Point B is at 2, 4. We go over 2 on the x-axis, up 4 on the y-axis, put point B. Point C is at -3, 5. We go over -3 on the x-axis, up 5 on the y-axis, put point C. There's our triangle ABC. Now we do the same thing with E, F, and G. So point E is at 4, 8. We go over 4 on the x-axis, up 8 on the y-axis, put point E. Point F is at 2, 2. We go over 2 on the x-axis, up 2 on the y-axis, put point F. And point G is at -6, 5. We go over -6 on the x-axis, up 5 on the y-axis, put point G. There is triangle EFG. Now again, we're trying to determine if the transformation from triangle ABC to triangle EFG is a dilation. To do that, we need to determine if all 3 pairs of corresponding side lengths are proportional. If they are, then the 2 triangles would be similar by the side-side-side similarity theorem, meaning that this would be a similarity transformation, meaning that it would be a dilation. So to figure out if all 3 pairs of corresponding side lengths are proportional, we just have to find the scale factor of all 3 pairs of corresponding side lengths. To do that, we need to first determine which of these is our pre-image and which of them is our image. Well, we're going from triangle ABC to triangle EFG, meaning triangle ABC should be our pre-image and triangle EFG should be our image. Next, we need to find the scale factor for all 3 pairs of corresponding side lengths and see if they come out equal. So you can start by finding the scale factor for any pair of corresponding side lengths here that you want. I'm going to start with segment AB and segment EF. Now remember, in order to create the scale factor, it's going to be the length of the side of your image over the length of the corresponding side of your pre-image. So in this case, that would be the measure of segment EF over the measure of segment AB. Now again, here we don't have a horizontal or a vertical line, so we can't just count. We have to use the distance formula for each of these. So we can start with whichever one we want to find the measure of first. I'm going to start with the measure of segment AB. In order to find the measure of segment AB, we choose one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plugging the coordinates to their corresponding spots in the distance formula and simplify. 2 minus -3 is going to be -1. 4 minus 7 is going to be -3. -1 squared is 1. -3 squared is 9. 1 plus 9 is going to be 10. So the measure of segment AB is rad 10 units. What about the measure of segment EF? To find the measure of segment EF, I choose one of these points to be x sub 1, y sub 1, and the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spots in the distance formula and simplify. 2 minus 4 is going to be -2. 2 minus 8 is going to be -6. -2 squared is 4. -6 squared is 36. 4 plus 36 gives you 40. So we end up getting rad 40, which we can actually simplify to rad 4 times rad 10. Now rad 4 times rad 10, the reason we do that is because 4 is a perfect square. So the square root of 4 becomes 2. So this breaks up into 2 rad 10. Meaning that if we were to create a ratio of our corresponding side lengths with the image over the pre-image, in this case it would be 2 rad 10 over rad 10. And the rad 10s simplify to 2 over 1. So the scale factor of this pair of corresponding side lengths is 2 over 1 or 2. But we're not done. We need to make sure that the scale factor of all 3 pairs of corresponding side lengths is the same. It should all be 2. So we go on to our next pair of corresponding side lengths, which would be segment BC and segment FG. Remember, in order to create our scale factor, it's got to be the side length of our image over the corresponding side length of our pre-image. So that would be the measure of segment FG over the measure of segment BC. So we can find either of these measures first. Doesn't matter. I'm going to find the measure of segment BC first. So the measure of segment BC I find by making one of these points x sub 1, y sub 1, and the other one x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the distance formula and simplify. -3 minus 2 is going to be -5. 5 minus 4 is going to be 1. -5 squared is going to be 25 plus 1 is going to be 26. Now rad 26 cannot be simplified, so we just leave it like that. Next, we find the measure of our corresponding image side. So that would be the measure of segment FG. So we choose one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the distance formula here and simplify. -6 minus 2 is -8. 5 minus 2 is going to be 3. -8 squared is going to be 64. 3 squared is 9. Add those together, you get rad 73. 73 is a prime number, so we leave it like that. We then create our scale factor as rad 73 over rad 26, and that does not simplify any further. So this would be the scale factor for this pair of corresponding side lengths. Now the issue with that is that this scale factor does not match the scale factor we found with the other 2 pair of corresponding side lengths, meaning all 3 pairs of corresponding sides are not going to be proportional. Therefore, this cannot be a dilation, and you can just stop right there. You're done. Now example 4 says if triangle ABC is similar to triangle AYZ, find the missing coordinate. Now you can see in our figure down here, we have 2 similar triangles, triangle ABC and triangle AYZ. We are missing the coordinates for point C. Well, we know one of the coordinates, right? We know the y coordinate has to be 0 because point C is on the x-axis. Well, that was easy. So we just need to figure out the x coordinate, which would be this distance right here. So if you think about this, because I'm given 2 similar triangles and the only thing I don't know is this distance right here, or this side length of our triangle, what I can do is set up a proportion based on these similar triangles to solve for this missing side length. And how do I do that? Well, I know, because these 2 triangles are similar, that the measure of segment AB over the measure of segment AY has to equal the measure of segment AC over the measure of segment AZ. So now we just have to plug in what each of these measures are equal to. The measure of segment AB would be this distance right here, which we're going along the y-axis, meaning it's going to be the distance between y values. So from 0 to 4, that means that this distance, the measure of segment AB, has to be 4 units. The measure of segment AY, again, we are going along the y-axis, so it's going to be the distance between the y values. So it would be 12 units from point A to point Y. For AC, the measure of segment AC, that's what we're trying to find. So we're just going to call that x. And then the measure of segment AZ would be the distance along the x-axis. So it would be the difference between the x values here. So 0 minus 9, that's just going to be 9 units. So now I can plug in each of those corresponding values to this proportion over here. The measure of segment AB is 4 units. The measure of segment AY is 12 units. The measure of segment AC, we don't know. We're going to call it x. And the measure of segment AZ is 9 units. We're going to put that in there. Now we just have a proportion that we have to solve. We know how to solve proportions. We just use the cross product property, multiply across, and set the 2 products equal to one another, and we can solve for x. So we're going to go 4 times 9, set that equal to 12 times x. We then solve for x by dividing both sides by 12. We get x is equal to 3. But we're not done. We're trying to find the missing coordinate. We need to answer our question. So C would be at what point here? Well, we said the y coordinate was 0. Our x coordinate we just found to be 3. So C is going to be at 3, 0. And you're done.
As Schmeichel Phelps always says, when you're winning at life, you're the best at what you do. You try.
Okay, doing the same thing here, except this time we're given the big triangle ABC is similar to the little triangle DEF. And we are trying to find the coordinates for point A and for point C. Well, since each of these points lie along the x-axis, we know that the y-coordinate for each of these points is going to be 0. So we just have to find the x-coordinate for each of these points, meaning we have to find the distance that point A is away from the y-axis and the distance point C is away from the y-axis. Well, the way we're going to do this is again with similar triangles. Because we have 2 similar triangles, this big triangle and this little similar triangle, that are both isosceles triangles that are are straddling the y-axis, that means that this distance from A to our origin and from C to our origin is equal, meaning we just have to find this side length, the measure of segment AC, divided by 2, and that should give us each of these measurements here. So let's create a proportion in order to solve for the measure of segment AC. And the way we're going to do that is by using the ratio of the height or altitude of each of these triangles. Remember, the ratio of the altitude is equal to the ratio of the lengths of the corresponding sides of two similar triangles. So we can say that the measure of segment HE, which is the altitude or height of our small triangle, over the measure of segment HB, which is the altitude or height of our large triangle, has to equal the measure of segment DF, which is the base of our small triangle, over the measure of segment AC, which is the base of our large triangle. We can then plug in what each of those measures are equal to. To find the measure of segment HE, because each of these points are on the y-axis, we just look at the difference between the y values. So this distance right here would be 3 units. So the measure of segment HE is 3 units. Same thing for the measure of segment HB. Because points H and B are both on the y-axis, we can just look at the difference between the y values to get the distance between these 2 points. So 15 minus 0, that's just going to be a distance of 15 units. Now let's look at the measure of segment DF and the measure of segment AC. The measure of segment DF, we see that D is at negative 2, 0, and F is at 2, 0. So the difference between these two x values, because both of these points lie on the x-axis, would be 4. Therefore, the distance from point D to point F is 4 units. The distance from point A to point C, we don't know, so we're going to call that x in this case. Now all we have to do is plug in those given measures to our proportion over here. Since the measure of segment HE is 3 units, that goes in there. The measure of segment HB is 15 units, that goes in there. The measure of segment DF is 4 units, that goes in there. The measure of segment AC is x, that goes in there. Now we have a proportion that we can solve, and we know how to solve proportions. We use the cross product property. Cross product property says we multiply across, set the two products equal to each other, and we can solve for x. So 3 times x is equal to 4 times 15. We then solve for x by dividing both sides by 3. We get x is equal to 20. But that's not our answer. We're trying to find the missing coordinates over here. So to find these coordinates, again, we know the y coordinates of each of these points is 0 because each of these points is on the x-axis. The x coordinates, though, we find by knowing that this triangle ABC, is an isosceles triangle that is straddling the y-axis, meaning the y-axis is cutting it perfectly in half. Because of that, it's bisecting segment AC down here. So if the measure of segment AC is 20 units, that means that each of these measures, the measure of segment AH and the measure of segment HC, both have to be 10 units. Because the measure of segment AH over here is 10 units and point A is on the negative part of the x-axis, that means that point A would have to be at negative 10, 0. Since the measure of segment HC is 10 units and point C is on the positive part of the x-axis, that means that point C would have to be at positive 10, 0. So your answer here would be that in order to make these two triangles similar to one another in this particular figure, point A would have to lie at negative 10, 0, and point C would have to lie at 10, 0.